So in this video, we're going to look at the log rule for integration that we introduced in the previous video. And we're going to look at three examples where we use u-Substitution to help in the solution process. So the first example is the antiderivative of 1 over 6x minus e dx. And like I've mentioned before, when we introduced u-Substitution, most of the time if you're doing a u-Substitution, you could do the problem without one, and the u-Substitution is there to make things easier to think about. So in this case, what I want to do is use the substitution u equals 6x minus e. I'm going to let u equal the denominator. And I'm going to do that because the derivative of the denominator, if I take du dx, I'm going to get 6, which differs from the numerator, which is a 1, by only a constant. And this was the key when we were working with u-Substitution. Most of the time you're looking for that derivative to differ from another expression by just a constant. So in this case, if I multiply both sides by 1/6 and multiply both sides by dx, I get that dx is the same as 1 over 6 du. So I'm going to come over and make my substitution. It's going to be 1 over 6x minus e is u. And then I'm going to replace the dx with 1/6 du. But the 1/6 is a constant and can be factored out in front of the integral. I'm now going to integrate. So I'm going to get 1/6 the natural log of the absolute value of u du. So again, if you have a form crap prime over crap, you know that the integral is going to be the natural log of the absolute value of the crap. And we do have that form because the derivative of u with respect to u is just 1. So we have a crap prime over crap form. We integrate. I don't know why I put a du there. We integrate, and then we add on our constant of integration. And then once we've added on our constant of integration, we're going to take and substitute back in for u the substitution that we made to begin with. So we're going to get the absolute value of 6x minus e plus the constant of integration. So this is example 1. Notice this is a linear function inside of the absolute value. So the linear function can take on negative values. So we want to leave that absolute value symbol in place. So example number 2, we have the integral of x squared plus 1 over x cubed plus 3x dx. And when you're integrating rational functions or ratios of polynomials, the first thing you always want to check is to make sure that the degree of the numerator is less than the degree of the denominator. And if it isn't, in general, you want to do a long division and rewrite the rational expression using long division. So in this case, I have a second degree polynomial numerator, a third degree polynomial denominator. I'm going to go ahead and run with what I have. In this case, I'm going to do the substitution u equals x cubed plus 3x. And I'm going to do that because du dx is going to equal 3x squared plus 3. And if I factor a 3 off of this, I get 3 times x squared plus 1. So in this case, the u-Substitution is sensible or reasonable because the derivative of 3x squared plus 3 differs from the numerator x squared plus 1 by only a constant. So now I'm going to multiply both sides by 1/3, which will give me x squared plus 1 on the right hand side and a 1/3 on the left. And then I'm going to multiply both sides by dx, which is going to give me 1/3 du equals x squared plus 1 dx. And now I'm ready to make my substitutions. I'm going to get the antiderivative of, I'm substituting x cubed plus 3x with a u. So I'm going to get a u in the denominator. And then the numerator, the x squared plus 1 dx, x squared plus 1 dx is getting replaced with 1/3 du. So here goes my 1/3 du. And now I'm ready to integrate. So I'm going to get 1/3 I have a u prime over u form. So I'm going to get the natural log of the absolute value of u plus a constant of integration, and then substitute back in. So 1/3 times the natural log of the absolute value of x cubed plus 3x plus the constant of integration. So we'll do one final example. So here I have the integral of 1 over x times the natural log of x squared, and this is dx. And in this case, I'm going to let my u equal the natural log of x squared, and you'll see why here in a minute. So I get u equals the natural log of x squared. So if I take du dx, I'm going to get 1 over the crap times crap prime. And what we want to notice is that the degree that we get in the numerator, because this is a polynomial inside of the natural log, the degree here is 1 less than the degree here. So this is going to simplify down to 2 over x. And here I have a 1 over x. So when I do this u substitution, u equals ln of x squared, it differs from what I have in this expression, 1 over x, by only the constant 2. So I have du dx equaling 2 over x. So I'm going to multiply both sides by a half. And then I'm going to multiply both sides by dx. So I'm going to get 1/2 du equaling 1 over x dx. So that's just by applying algebra to both sides of this equation right here. And now you're ready to make your substitution. We get 1 over ln of x squared is just u, and then 1 over x dx, 1 over x dx gets replaced with 1/2 of a du. The 1/2 is a constant and can factor out front. Now I have a crap prime over crap form. So I'm going to get 1/2 the natural log of the absolute value of u plus a constant of integration. And then I just need to substitute back. So I get 1/2 the natural log of the absolute value of the natural log of x squared plus a constant of integration. So it looks a bit yucky, but it's good enough for government work.